All right, I'm pleased to introduce Nico Weber and Hans Wennborg, and they'll be talking to us about Chromium and Clang.
Thank you very much. Okay, so my name is Hans.
Hey guys, I'm Nico, and we're beyond excited to share some of our experiences with using Clang with the Chromium project.
Yeah, so apart from lots of people here, we don't actually work on Clang or LLVM. We actually work on the Chromium web browser project.
And Chromium is the open source foundation of Google Chrome, which is a web browser that's cross-platform that runs on Windows, macOS, Linux, and also compiles on all these platforms, obviously. The main difference between Chrome and Chromium is really just the name and the color of the icon. So Chrome is roughly Chromium, and all of Chromium is open source. And yeah, that's that.
Yeah, and we don't have nearly as much source code as Chandra and his team, but we still think we have a lot of source. We have about 5 million lines of code in the Chromium repository itself, and then we pull in about 5 million lines more in various third-party libraries. So we use WebKit for rendering and parsing HTML. We have V8, which is our JavaScript virtual machine, and then we have quite a long tail of different smallish libraries like libpng and libjpeg and so on. Yeah, so that's about 10 million lines of code. That's one line for each person in Sweden. And each full compile that we do, we build about 10,000 objects.
In addition to having a bunch of code, we also have many people working on Chrome. So in the last year, we had over 600 committers according to Git log. That's like more than 2 committers per day if you need a new person per commit. So because of that high churn rate, we strongly believe in using great tools. We build all our code with -w all, so we enable all warning that we can find. We build with warnings as errors. We use static analyzers such as Coverity. We use dynamic tools such as Valgrind. We have opt-in crash reporting in Chrome, so if Chrome crashes on a user's machine and they agree to send us their crash reports, we'll get the stack where the crash occurred. And Clang is one of the tools that we started using.
Right, so we're going to go through the timeline for when we started using Clang. We tried to dig out the first patch that actually mentioned Clang in its description, and we found one from December 2009, which we think is pretty early. That's before LLVM 2.7 and before the C++ support in Clang was even considered alpha quality. And since then, in last year, we spent quite a lot of time trying to get our code base to compile with Clang. We fixed a bunch of warnings, because Clang found more things to warn about. We had to make our code actually conform to C++ a little bit better, at least, because Clang was much more strict than the compilers we'd been using. And we also ran into a few bugs in Clang and LLVM, which we filed, and that got fixed, and so on. And in September, things started to actually work. So first we had the Linux build working with some warnings disabled, and then a couple of days later we had the Mac build working as well. And this is not actually switching to Clang. This is just like compiling with Clang in addition to the other compiles that we do. And to make this stick, we added a build bot to our build infrastructure to actually build with Clang continuously, so we get notified if someone checked in something that broke our build.
And that looks like a long time span to just get a project to build, but that was 3 of us doing this like every now and then, so we didn't actually work half a year non-stop on getting Chrome to build with Clang, but one of us did like a patch in a week and then waited 3 weeks and then upgraded Clang and see how much more C++ support there was. So that's not active work time.
No, we like to think that for like a full-time engineer, it would be like 1 or 2 weeks of work. Yeah, so before last year's developers meeting, LLVM 2.8 was released and C++ support was considered complete. And we think it was certainly working for us, and Clang was happily building away. So we started looking towards doing other things with Clang as well. We wrote our style plugin, which we'll be talking about later. We moved our build bots to the main waterfall. So if you actually broke the Clang build, we would close the tree, and the guy watching the tree would get angry and email you and revert your patch and so on. It was really like a first-class citizen of Chrome. And then we added a build bot for our Chrome OS as well.
Yeah, so far we got our code building with Clang. We started building tools, and so the next step was to actually ship the binary produced by Clang, at least on macOS. So over the last 3 months, we gradually moved all our Mac infrastructure from GCC to Clang. 3 months ago, we moved all the bots that built the Chrome that ships to users to Clang, and once it looked like this will actually stick and there aren't any showstopper problems, we moved our Mac developers over. And just 1 month ago, we released Chrome 15, which is the first stable Chrome release that's built with Clang on Mac. And the culmination of our efforts so far are the opportunity to give this talk at this meeting. So let's talk a little bit about what we get out of using Clang. And after that, we'll talk about some of the practical concerns, benchmarks, and so on. So we think there are really 3 reasons for us to use Clang. The first one is that the diagnostics are awesome. That's, I think, widely acknowledged. The second thing is that it's very easy to build tools on top of Clang, and we built a couple of tools, and we'll talk about some of the tools that we built. And the third reason we think Clang is awesome is because we really like the Clang community and the upstream. We think you guys are really fun to work with. And so let's talk about the first thing, diagnostics. So we like warnings because of many reasons. They look pretty because of colors and very precise location. They find real bugs. A good set of warnings is on by default if you just build without any flags or if you build with -wall. And they find real bugs. So let's look at a few examples. Here's a pattern that's fairly common in Chromium, and I guess in most object-oriented code bases. You have a class C with a virtual function foo, and you have a class D that overrides this function foo. And then the guy who wrote C, the class C comes along and sees that his foo doesn't actually change any member variables in C. So he's like, hey, I should add a const for that. And he doesn't tell the guy who wrote D. And now D foo no longer overrides C foo because it's no longer the same method signature. And that's a very fairly frequent bug in Chrome. And let's see what happens if you build this with with Clang -wall.
So it turns out that there was actually a warning catching this when the signature of the function in the superclass changes. The function in the derived class is actually no longer overriding it. But they still have the same name, right? So it's an overload instead. And that turns out to be a pretty bad idea in general in C++ to overload a virtual function. And Clang has a warning, so it turns out that it catches this thing as well as other things. And GCC has the same warning, but we can't really use it because it turns out that that's slightly more noisy and warns about a few cases which we don't consider to be bugs. But the Clang warning is spot on. And when we turned this on, we found 30 or so bugs in Chromium and WebKit. And there's been some weeks when we had this turned on and we found basically a bug every day. Someone was trying to check in and Clang build went red and we said no and they had to revert. So this is a good warning.
Yeah, and it solves half of the override problem basically for free just by building with Clang -wall. The other half of the override problem is slightly less serious if the guy who wrote C removes his foo and the guy who owns D thinks his foo still does something useful. If you add the override annotation, then that's fixed too. So for this, you need to actually change your code. You need to add override at the end of your function signature. That's a C++ 11 feature that Clang supports as an extension in C++ 98, which we use. And we slowly started rolling that out. We were kind of skeptical if it would work out at first, but turns out this is extremely, extremely useful in practice. So by now, I think about 10,000 functions in Chrome are annotated with override. And just this week, we decided that every time you have a virtual function that overrides a function, you have to mark that as override, at least in the Chrome core code.
Okay, so this is a more silly warning that we still like. We found this typo in the code somewhere where someone had actually ended up using the or assign operator instead of the not equals operator. And it's kind of funny because they're not really close on the keyboard, but I suppose they look a bit similar. So we figured, okay, maybe the compiler could warn about this. It would be really easy. It probably won't catch anything, but let's do it anyway. And it was easy to do. We did it basically like Doug described how to do it earlier this morning. And we checked it in, and it turns out that it did find a bug in LLVM itself, actually. So we think this is a valuable lesson, that this long tail of maybe silly but still good warnings is extremely useful because, it helps developers everywhere.
Yeah. So if you have a warning that fires once in a million lines, then it fires 10 times in Chrome. All right, so here's another warning of the same pattern. So we found that someone in Chrome wrote x plus some boolean and then the ternary operator. And what he intended was see if the boolean b is true. And if it's true, then add y and else 0 to x. But as it turns out, that plus has a higher precedence than the ternary operator. And so we figured, oh, that's somewhat surprising. Maybe we should add a warning for that, and maybe not. Maybe it's very noisy if we add this. So we just implemented the warning and then built all of Chrome with this warning set and all of Clang with this warning set. And it turns out every time this warning fires, it's actually a bug. So it turns out this is a useful warning. And so we upstreamed that. And this is probably like the one single good thing about a huge code base is that you can evaluate warnings. So here's yet another example of this pattern to when you find a bug, don't just fix the warning, also let the compiler find the bug so that the bug never happens again anywhere in the world. So a pretty common pattern to zero out a struct is to do memset pointers to struct, 0, and then size of star struct. And if you leave out the star in the size of expression, then the size is just the size of the pointer and not the size of the struct, right? And then this only sets the first 4 bytes of the struct to 0. And this is a bug that we found in the MD5 code in somewhere in Chrome. And as it turns out, when we implemented this warning, we found that this MD5 function had been copied into, I think, 5 third-party libraries that we use, and they all had this bug. So this not only showed us a bug, but also like a layering weakness, I suppose. So we implemented this warning and ran it on our code base, and it turned, for us, didn't have any false positives, so we checked it in, so all good, right? Turns out the owner of another huge C++ code base wasn't so happy with this warning. And so what they did, they actually changed our implementation of the warning to work for them as well and still find all the bugs that we found. So another success story for open source, I suppose. And that's it with warnings. So the second thing we really like with Clang is tooling. So let's look at a few tools that we built.
This is really, this ties into what Doug said earlier today as well, that Clang is more than a compiler. It actually allows you to build all the tools you dreamt of building if you had a programmable compiler, and we think that's awesome. So let's look at a few tools we built. The first one is our Chrome style checker plugin. So for Chromium, we have these style guidelines, like many projects do, and they tell you where to put your curly braces and whatnot. And we try to check for this, like reviewers are supposed to catch it, and we have a pre-submit script in Python that checks for things. But some of these things are really hard to check with Python. For instance, we have this guideline that you're always supposed to explicitly mark a function virtual if it's virtual, because we think that makes the code easier to read. And that's hard to check with the Python script, but it's very easy to check with Clang because the compiler knows, right, if it's virtual, and it can see if did the programmer actually explicitly make it virtual, and if not, then we can issue a warning. So that's very easy. And another one is that we don't allow people to define complex constructors and destructors inline in header files. We think it's a bad idea because then everywhere that header file is pulled in, it gets into the object file, and then the linker has to sort out the mess at the end. So we warn about this. It's easy again to do with Clang, and when we applied this, we found a bunch of instances of this in a gmock, which is a test library that we use. And it turns out that fixing those issues sped up our compile with like 25%. Because we were building 16 files in parallel, and we ran out of memory because of these inline constructors and destructors and started swapping. So yeah, this was a great improvement.
So this style checker is actually implemented as a Clang plugin. So we use a vanilla Clang without any changes, and then we have a third-party plugin that we load via the plugin API at runtime. And we don't think writing plugins is as hard as all you guys say. So we think it's not too bad. And also the guy who wrote the style checker plugin first tried to do this in GCC, and he couldn't figure out how to build GCC in over a day. And now this is a Clang thing. Here's another example from V8. V8 is the JavaScript virtual machine in Chrome. And JavaScript is a garbage collected language, which means there's some function in V8 that basically does garbage collection, which frees up some JavaScript objects and moves around other JavaScript objects. And so V8 has pointers to these JavaScript objects. And if that's a raw pointer and the garbage collection runs, then the pointer may become invalid. So what they have this handle smart pointer class, I guess, and that's a pointer that survives garbage collection. So if you have a handle to a JavaScript object, and then you run a garbage collection, and the garbage collection moves around that object, then the handle now refers to the new location, and also understands if an object is deleted. But for performance reasons, they use raw pointers in a few points in their code. And then they have to be very careful to not access the raw pointers after something triggered a garbage collection. So if you look at this code, foo is a function that returns a handle to an object, and bar is a function that takes 2 raw pointers. And then at the calling side, you have a handle bars, and then you call a bar by first calling foo, which might trigger a garbage collection, then dereferencing the handle, which gives you a raw pointer, and then dereferencing bars, which also gives you a raw pointer, and this should be safe. But as you guys all know, the evaluation order of parameters in a function isn't well defined, so the compiler might instead convert bars to a raw pointer first and then do the garbage collection and then call bar, and that might crash, right? And it turns out these bugs are very tricky to debug. We have historically been bad in catching this in code reviews. So one guy on the V8 team basically wrote a Clang-based static analyzer that proves that that no raw pointer is defined before something that can garbage collect and then used after something that garbage collects. And this kind of tooling is just impossible to build without a smart, programmable, flexible compiler.
Right. So these plugins both looked at the code and issued warnings, but we also wanted to do rewrites. For instance, we had this smart pointer class, and we wanted to replace all the implicit constructor calls and make them explicit. And we figured this should be pretty easy to do with a plugin, and it worked well at first. We fixed a couple of 100 instances, but then we ran into trouble and eventually had to give up because it turned out to be actually too hard for us. We had another example where we had written this new callback mechanism for Chromium, and someone figured, hey, let's update all the old code using a tool. They based it on the arc rewrite system, and I think a colleague of us spent 4 days trying to do this, but that was apparently too hard as well. So yeah, we really hope that it would be easier to do rewrites, because it feels like it kind of almost works, and it's so desirable to do this. So yeah, if it could be made easier, or if there could be tutorials and stuff telling us how to do it, we think that would be awesome.
And last tool that we want to mention, so we have a couple more tools, we're not describing all of them here, is Address Sanitizer. Address Sanitizer is a dynamic memory checker which checks invalid reads and use after freeze and all that. And it's kind of like Valgrind, and its claim to fame is that it's 10 times as fast as Valgrind, which means you can now use it for many more things. So you can run Valgrinds on your unit test, that usually works, but you can't use it on, I don't know, full browser tests that start up a full Chrome instance, because that's just too slow. And ASAN was written by Kostya, who sits there, and the great news is that he's giving a talk about this at 4:30 over there. So this is a great tool, found many, many bugs in Chrome, and I'd encourage all you guys to go to Kostya's talk later.
Right, so let's discuss some practical concerns. Like the first one might be, which Clang version should you actually use? There are a lot of emails on the mailing list where people mailing and something isn't working, and people ask back, like, which version are you using? Oh, it's 2 years old. And the reply is usually, like, you should probably be using Clang from trunk instead. And that's exactly what we do. We use Clang from trunk. We don't have any local patches. We basically want the latest and greatest stuff straight away. And also, if we do contribute something upstream, we like to get it back within a week so we can use it straight away. So what we do is that we basically pick a revision each week, and we pull that in, compile it, and we compile all of Chrome, and we run our tests and so on, and we coordinate a little bit with other people at Google who know things about Clang. And if it looks good, we use it, so we build it and we upload it to this server, which is actually a public server here, so you can use it if you like. And then all our developers machine and build bots and so on, they pull this in automatically and use it for that week.
And another advantage of this is that we basically help Clang, we'd like to think, because we find bugs in Clang pretty quickly after they're fixed, so at least serious crashes we find pretty reliably, I think.
Yeah, it struck us that this might actually be kind of a crazy idea, because we're using a compiler built from trunk to ship a web browser to millions of users, And yeah, maybe that's a little bit dangerous, but we have great faith in you guys. And and you know, we think we have good tests, good test coverage, and good tools like the crash reporting tools and so on. So it seems like this actually works, and we think it's kind of a good thing for the community as well, because you know, we catch some issues this way. It's pretty cool. And let's look at some numbers. So this is for my my Linux workstation, which is it's a nice workstation with lots of CPU and lots of RAM. And this is building the Chrome target, not the test, just the actual browser. And it turns out that Clang is faster, which is nice. It's about 30% faster for the release builds and slightly faster for the debug builds. And we think this is really, really good, because it used to be that it was actually slower for debug builds. So our developers kind of had to make the choice between, you know, all the greatness of Clang or slightly faster builds. And that was a hard choice to do, actually.
On Mac, Clang has it slightly easier because it only needs to compare to GCC 4.2, which is the latest GCC that Apple ships on Mac. And I don't have up-to-date numbers for this because we switched all our infrastructure off GCC like 3 weeks ago, and so already Chrome no longer compiles with GCC 4.2. I ran some numbers 6 months ago, and back then debug builds were about 30% faster to build than with GCC, and release builds were like twice as fast or something like that. And this is just build time, not execution time.
Right. And then we looked at binary size. And so this is back on my Linux workstation again, and this is comparing with GCC 4.4, which is the GCC we would otherwise be using. And for release builds, we found that the sizes were actually similar, so there wasn't much to report there. And these numbers are for debug builds, and there we found that Clang's binaries were a bit larger than GCC's. So for the object files, it's about 80% larger, and for the final binary, it's less, but it's still a difference between like 1 gigabyte to 1.5. But we're not too sad, because it used to be much worse. We used to see the Clang object files being like 5 times larger than GCC's, and this slowed down the build a lot. So as long as the build is as long as the build time is on par with GCC, I think we're pretty happy. But it would still be nice to close this gap a bit if that's possible.
And again, on Mac, the numbers look a little bit better. The great news is that the release binary is 10% smaller with Clang, which is actually 10 megabytes for Chrome. And after zipping, that's like 3 megabytes. And since all of our users need to download Chrome, that's actually a big deal for us. So for people on slower connections, that's quite a bit of safe download time. Debug binaries, I think, are 10% bigger in Clang, but who cares about debug binaries, I suppose. And so here's a small interlude about build times. So as we said, when you build all of Chrome, not just the browser, but all test binaries and so on, you end up compiling about 10,000 files. And if you assume that you have a fairly beefy machine with 16 cores and enough memory for everything, which is about 16 gigabytes of RAM, 12 gigabytes are not enough, and you assume that one file takes about 2 seconds to build, then under these ideal conditions on a very fast machine, you need 20 minutes to compile everything, which is a pretty long time. But if you instead assume that you have a distributed build system which with about unlimited parallelism and a .o file size of about 50 kilobytes and a downlink of about 3 megabytes per second, then it only takes about 2.5 minutes to download all the build artifacts. And it turns out we actually do have a build system like that. So our builds are 10 times faster if we do distributed sizes. And our distributed build time scales with .o file size. So for us, .o file size actually matters. And the speed of Clang doesn't matter at all, because everything's compiled somewhere else and we have unlimited machines in practice. So many developers, of course, still build locally because setting up distributed builds is a little bit tricky. So it's still very useful for them that Clang is fast, but for all our production machines, .o file size is where the speed is at.
Okay, so what about performance? That's kind of, it's all about performance. We like to think that Chrome is the world's fastest browser, and we kind of like to keep it that way. So we track performance very carefully. We have about 15 or so different performance benchmarks that we run continuously and watch for any change. And this is the V8 benchmark, I think. And this is from the time when we switched to Clang. This is on Mac, by the way. This is from the time that we switched the build over to Clang. And the point with this diagram is that you can't actually tell where the switch happened. So we were pretty pleased about that it just works so seamlessly to make the switch.
Yes. So you might think the score goes up a little bit at the right, but that's something unrelated. The actual switch happened somewhere about here, I think. And so on all our benchmarks, we couldn't see any performance regressions or improvements when we switched to Clang. So for the V8 benchmark, that's probably because all that code is jittered at runtime anyway. But some of the benchmarks do actually measure stuff that's influenced by the compiler. So Clang used to be lower on one of these graphs than GCC because we used to build with -02 with Clang, but -03 with GCC. Because Clang used to crash with -03 and then got fixed, and then we switched, and then that was at the same height. So the same performance at 10% less code size, that's pretty nice. We did see some slowdowns when running our browser tests or when running some of our test suites, but only in debug builds. So this is where we switched to Clang, and our execution time went up by about 2 minutes, which is about 10%. So there's something slower there. Maybe Clang is just better at honoring -00, the don't optimize my code, please. So I know some instances where GCC does optimize code if you tell it not to. I tried to track down what that is, but we never really found out. But it's just in debug builds, so we can live with that.
Okay, so to conclude our talk, we really love Clang. We love the diagnostics. We like the code base. We can actually, at least we think we can actually understand it and do things in there. We like the way the Clang project is run. We think it works pretty well for us. We love using Clang to write our own tools. It's really cool when we succeed, at least. But it would be nice if it were just even slightly easier to write tools, especially rewriters. We really like that.
And that's it. So we have a mailing list, clang@chromium.org, if you want to send us any questions. We have a wiki page that describes how to build Chromium with Clang, if anybody ever feels like doing that. It's great fun. And now ask us questions. Thanks, guys.
A lot of browser benchmarks or JavaScript benchmarks.
Yes.
Did it, so time is spending in this code is still in changing compiler.
Mm-hmm.
Do you have any data on DOM benchmarks?
Yeah, so we have a whole suite of benchmarks. Some of them measure just the V8 benchmark or Kraken or something like that, which only measures the JavaScript performance. Some benchmarks measure DOM performance, some measure startup time, some measure some browser UI performance. So we have all kinds of benchmarks, and they all showed no change on Mac. Yes?
Regarding the object file sizes, are those object files native code files, or are they LLVM code files?
No, they native ELF files. So the question was, is the difference in the file size in the code or in the debug information? And I think it's all debug information. The code should be pretty similar. Chandler?
Have you looked at doing any link time optimization?
Have we looked at doing any link time optimization? Not really. I think Rafael Espindola blogged about this for doing this on Firefox and saw moderate losses when doing this. So I haven't tried it yet. Do we have any experience how the debug experience is? So GDB seems to work fine. When we switched to Clang, the thing that parses debug information for our crash service at first didn't understand the debug information written by Clang, so we needed to patch a breakpad. But after that, things look fairly normal.
Just a comment, thank you for your new warnings. They also caught a lot of bugs in other large code bases.
The comment was these new warnings also caught many bugs in other large code bases. Hooray. More questions, come on guys. Chandler?
What kind of cake do you want?
What kind of cake do we want? That's an excellent question. Anything that's sendable through email, I suppose. What's that? So we switched to Clang on Mac. What about other platforms? So we are not actively thinking about this. GCC seems to work fairly well on Linux. And on Windows, Windows and Clang is kind of not completely done yet. We'd like to work on getting at least a compiler on Windows for the diagnostics. So that's probably what I'll look at next. Is the style checker open source? Yes, everything we showed is open source. So if you go to codesearch.chromium.org, you can just paste in your favorite, search for Clang : I suppose, and that will probably find all our Clang plugins.
More of a comment. The O0 performance difference between their LLVM uses a different instruction selection algorithm and register allocation algorithm. O0 sure does have actual optimization, whereas GCC doesn't do any high-level optimization. It uses the same code generation. If that matters to you at O0, you can sacrifice some optimization time and have a turn path.
So that was the comment. Okay. That was a comment that Clang uses a different instruction selection algorithm and so on. If you add -O0 while GCC doesn't, which might explain the 10% code execution time difference, and we could try playing with that, but I don't think it's very important. Yes?
Any comments on profile guided optimization? Do you do PGO on the GCC case?
Any comments on profile guided optimization? We don't do PGO on Linux or Mac. I think we do it on Windows, but it takes terabytes of RAM or something like that. Or not quite terabytes, but a lot of RAM. So we don't do it anywhere else at the moment. But I think we have a team looking at doing that somewhere.
So you switched over compiler to Clang. Have you considered switching the C++ standard library over to libc++?
So we have switched the compiler. Have we considered switching the standard library to libc++? So as far as I understand, if we want to use the dynamic library part of that on Mac, we need to target line or later. And we ship the same binary to 10.5, 10.6, 10.7. So that is not an option. We can probably statically link in libc++ and get that, but we haven't really looked at that yet. All right, then thank you for your time.